Welcome to Stat 310 Lecture 9. So today we're going to go into more details into Chapter 8. And so just a reminder that depending on when you see this, so homework number 3 is due Thursday, September 24th, and the homeworks continue to be due every week after that. So what we're going to cover today is we're going to kind of like round off our discussion on the method of moments estimation. So we're going to go into that in a little bit more depth. We started to talk about it in the previous lecture. So today we're going to talk about it in more depth. So in particular, we're going to focus on the case where you have more than one parameter. So we saw examples where you had a single parameter and how you use the method of moments in the previous lecture. And so we're going to see that in more general cases today. And then we're going to talk about another aspect that's pretty important, which is confidence intervals and standard errors, which is kind of the other thing we need to think about when we're trying to develop estimators. And these are all in sections 8.4 of the textbook. So just to remind everyone of the framework, in particular the context of chapter 8. So our sample data here is x1 through to xn, as it typically is. And then for the second component, the distribution or the parameters, we have xi's indexed, like it follows some distribution indexed by parameter or parameters theta. And I should also say here that we're typically going to focus on the case where the xi's are independent. And theta is our parameter of interest, and p is the underlying distribution. So it could be a normal, a uniform, an exponential, or some other distribution. Okay, and so we're going to the third component is the estimators or statistics. And so this week we already talked about the method of moments, but we're going to talk about that in more depth today. And then in the next lecture, lecture 10, we're going to talk about maximum likelihood estimation. So these are the two most important and general estimation procedures that we're going to learn in this course. So this gives you a way to estimate parameters from data in a general way. And so then, the next key, component, and we'll focus on really components 4 and 5 today as well, which are the distribution of the estimator. So in particular, could we determine like an asymptotic or an exact distribution of the estimator? Typically for the method of moments, we're not going to be able to do better than an asymptotic distribution in most cases. And then using that distribution, the fifth component is, can we provide kind of confidence intervals or some other inference from based on the parameter theta hat or the estimated theta hat. Can we say anything about the parameter theta? So sorry, a theta hat is a statistic or an estimator, which depends on the data, and theta is a parameter. And so what can we say about theta hat with respect to theta? So I just wanted to remind everyone of the method of moments. So here I only focused on the case of a single parameter. So say you have a parameter theta to estimate, and how do we do that? So the method of moments is based on using the moments, so the mean, the variance, and so on, to actually use those, because we know how to compute those from the data. So use those statistics to then calculate estimators. And so the basic idea is that the procedure kind of has 3 basic steps. Firstly, we work in the population domain. So step 1's all actually, there's no data involved, it's just in the population domain. And steps 2 and 3 are in kind of the sample data, involve the sample data. So in the population domain, you can calculate the mu with respect to theta through the function h. Let me just make this neater. Okay, so you can work out the population mean and how that relates to the parameter theta. And then you can invert that expression to get theta in terms of mu. And this inversion is what we're going to use to calculate the method of moments estimator. And then, then we use the data. So you know what the sample mean is, mu hat, which is, the 1 over n summation xi, or just x bar. And then theta hat mm is just g of mu hat, or equivalently just g of x bar. Okay, and so this is kind of how we apply the method of moments to the first moment, which is the mean. So, we saw various examples of this in the previous lecture. So, as an example, if we have xi is Poisson lambda, we know that lambda, which is equal to e of xi, is just equal to mu. So, quite simply, the method of moments estimator is just exactly the sample mean. And that's because, we just have this that g and h are both the identity functions. Another example we saw was the uniform. So we have the theta is kind of the right endpoint. Okay, and then we know that e of xi, so this mu here, mu is equal to theta over 2. So your h of x, we'll say, is just x over 2. That's the function we have. And so to invert that expression, that's pretty easy because this is just a linear expression. So we have that theta is equal to 2 mu. So g of y equals h inverse of y, which is just 2y. Okay, and then so therefore that means that theta hat mm is just is going to be 2 mu hat, which is equal to 2 x bar. Okay, and so that's how we would estimate the endpoint there using the method of moments. So note that the subscript denotes the method of moments estimator, because later we're going to see that we're going to use the maximum likelihood estimate, and so we want to distinguish between that. And then another example that we saw was exponential lambda. So we know that in that case that mu is equal to 1 over lambda. So here your h of x is 1 over x. And so if we want to invert that expression, then again, this is not too difficult, because to invert 1 over x, you just get 1 over y, or so this is just lambda equals 1 over mu. So your g of y is just h inverse of y, which is just 1 over y. So the key piece of math that you need to be able to do to work in this procedure, to use this procedure, is to be able to invert expressions. So first, be able to calculate expectations, which you hopefully are able to do from 309, and then to be able to invert expressions. So those are really the two key things, the two key kind of mathematics, calculus that you need to be able to do here. And so then clearly then we have that theta hat method of moments is just 1 over mu hat, which is just 1 over x bar. Okay, so that was just kind of going over what we did in the previous lecture. And then a natural question that you might think about, and that we certainly need to think about, is what so if we need to estimate more than one parameter, so say you have theta 1, theta 2, up to say theta k, one thing you might think about is, well, you can just find different expressions for mu, and then just write the different functions, kind of repeat these for mu, and then just repeat that for x bar, and just get different g's for each of the thetas. But this is not the best approach, because basically you're just reusing the sample mean over and over again. And so you're not kind of getting new information to estimate theta 1 through to theta k. And so So to kind of use our information in a more efficient way, we need to generalize to k moments. And so recall that so I believe you've seen this, but if you haven't, it's okay. I'll just remind everyone. Recall that the kth moment of a random variable is e of so I'll use this notation mu k is e of x to the k. Okay, so for example, mu2 is e of x squared, and that is equal to the variance of x plus e of x plus the mean squared. So you can think about that as being sigma squared plus mu squared. EC. So this leads to kind of the general method of moments procedure. So the general method of moments procedure. So here we have parameters theta 1, theta 2 up to theta k. So we're going to see some examples shortly where k equals 2. Typically in this course, you won't have to look at examples where k is bigger than 2. So typically most of the examples you'll see will be k equals 1 or k equals 2. But the procedure certainly applies for any number of parameters that you might be trying to estimate. So step 1 looks somewhat similar, but now we have k moments. So we have now, let me use this notation instead. Let's, okay, so let's let big K, so let me just be clear about this. So here, big K is the total number of parameters, and little k is the subscript. So we have here k equals 1, 2 up to big K. Okay, and so then we have that, now we have a multivariate function. So we have mu1, say mu1, mu2 up to mu big K is equal to h of theta 1, theta 2 up to theta k. And this is a big K, so we now have a, so h here, ooh, sorry. Sorry for this delay. Okay. Okay, so now let me switch. Okay, I got that sorted out. Sorry about that. So here, h here is now a multivariate function from rk to rk. We're going to see this specifically for k equals 2. So, we'll think k equals 2. So it can get pretty messy pretty quickly, but we'll see some examples for k equals 2 shortly. Okay, and so then we again have to invert that expression. So we're going to get theta 1, theta 2 up to theta k equals to g of mu1, mu2 up to mu k. Okay, where g is going to be equal to h inverse. So we're now inverting a k-variate function. We'll see how to do that shortly in some various examples. So now we can calculate we can find estimators of these moments, which are just these are the sample moments. Okay, so we're using the plug-in principle. So this is mu hat k. K equals 1, 2, up to big K. And then we have that theta hat 1, theta hat 2, up to theta hat K equals G of mu hat 1, mu hat 2, up to mu hat K. Okay. So now let's see this for a couple of examples. So we'll go back to kind of an example we've seen before, which is the normal distribution. So here we have theta 1 is mu and theta 2 is sigma squared. Okay, so those are the parameters that we're trying to estimate using the method of moments procedure. Okay, and so we know that mu is equal to E of xi. So that equals theta 1, which is very convenient. And then we know that sigma squared, sorry, let me just see. Let me write this consistently. So mu1 here, which is E of xi, is theta 1. And then mu2, which is a second moment, is E of xi squared, which is equal to, we know that that's sigma squared plus mu squared. And so that is equal to theta 2 plus theta 1 squared. So you can think about it as though, like, you know, mu1, mu2 equals to theta 1, theta 2 plus theta 1 squared. So this is really your h function. Okay, and so now we need to kind of invert that that expression to get expressions for theta 1 in terms of we want thetas to be in terms of mu, and in this case it's not too difficult because we can see that we have, you know, we want to get, so theta 1 is just going to equal to mu 1, and then because we you know, we know that theta 1 is mu 1, it's fairly straightforward to invert the sigma squared. We know that sigma squared equals theta 2 is equal to mu 2 squared and then minus mu 1 squared. So this is going to be mu 2 squared minus mu 1 squared. Okay. And so now let's apply step 2. So remember that so this is going to be our g function. Okay, so this is a two-dimensional function. Okay, so we know that mu hat 1 is equal to the sample mean, which is 1 over n. Okay, and then mu hat 2 is equal to 1 over n. So this is just, you know, the sample moments. So this is the sample moments. So this again kind of uses like a plug-in principle where, you know, we, rather than looking at E of xi squared, we just take a sample average of that, and that gives us an estimate or a statistic for that. Okay, so then we know that theta hat 1 here is just going to be mu hat 1, which is x bar. And then theta hat 2, so this is step 3. So theta hat 2 is going to be equal to mu hat 2 squared minus mu hat 1 squared. So this is just applying the function g here. And so that's going to be, sorry. And then minus x bar squared. And you can also rearrange this to see that this Okay, so this is the method of moments. So it turns out here that we have that mu hat method of moments is x bar. Oh, sorry, yep, is x bar. And then we have that sigma hat squared method of moments is 1 over n. Okay, and so you can see here that once again, we don't get the n minus 1 when we use this this method of moments procedure for sigma squared. Because remember that here we're just kind of using this principle. The reason that we had the n minus 1 originally was to get an unbiased estimate for sigma squared. But here we just get the 1 over n. So this is the method of moments estimate that we get. Okay, so that's just illustrating how we use the method of moments procedure when we have two parameters. Let's look at another example just to illustrate that. And again, you can see that the only real math involved here is calculating the expectations and calculating the expectations of the moments, and then and then being able to invert that expression to go from G to H, or from H to G. Now let's look at the example where we have so gamma of r lambda. So just to remind everyone what that looks like, that means that the parameters we have are has this PDF, so it's going to be so here we have r could be 1, 2, so on, and then lambda could be anything bigger than 0 here. So this is what the PDF looks like. And the domain of x here, or the range of x, or let me just so this expression holds for x is in okay. So now let's find we want to find r hat mm and lambda hat mm. Okay, so here our theta 1 is equal to r, and our theta 2 is equal to lambda. So if it's easier for you, I'll do this by just kind of using r and lambda. If it's easier for you to use the parameters that are already there, then that may be maybe that's easier for you. I'm going to do it for normal. I changed to theta 1, theta 2. For gamma, I'm just going to keep it as r and lambda. Just so that you can sort of see two different ways of doing it, and then you can decide which you find to be easier for you to execute. So we know. So first we need to calculate. So step 1 is to find mu1, which is e of xi, and mu2, which is e of xi squared. Okay, so. So this is something you can potentially look up. The calculation is also not too difficult to do, but it's going to be r over lambda. Okay, I'm going to just show you how it's done just quickly. So just so that you can kind of see this being done once. So the range is 0 to infinity here. So this is going to be okay, and I'm going to use a useful trick here, which is that you can rewrite this as r Okay, so all I've done is taken out an r and a lambda, which is constant with respect to x. So you can take it out of the integral, and you get and then you get an expression here that this is going to be 1 because of the fact that this is just this is the PDF for gamma of this is an r plus 1 lambda gamma distribution. So when you integrate a PDF, it's always 1. So mu1 is r over lambda. And then using a similar argument, so mu2, which is equal to e of xi squared, that's equal to so this is going to just be So what I'm going to do here is to try to get a gamma r plus 2 distribution out of it, which is exactly what we're going to see happen. And then this is just 1 since it's the PDF for a gamma r plus 2 lambda distribution. Okay, so we have that mu1 is equal to r over lambda. Mu2 is equal to r times r plus 1 over lambda squared. And another thing that's kind of you've potentially can look up or work out is that sigma squared is mu2 minus mu2 minus mu1 squared, which is equal to r over lambda squared. Okay, so this gives us essentially what the expression that we're looking for. So we have that mu1, mu2 is equal to r over lambda, and then r times r plus 1 over lambda squared. So this is our h function here. Now, if we want to invert this expression to get r and lambda by itself, so I think it helps here to use the sigma squared that we have here. So we know that mu1 equals r over lambda and sigma squared. So this is just a different set of we're just using we're going to be using mu2 the second moment through sigma squared. What we can kind of see from this, which is nice, is that lambda here is equal to mu1 over sigma squared, because you just get r over lambda squared, which is lambda. So we can see that r lambda is equal to mu1 over sigma squared. And then you can also see, and to re-express that in terms of mu2, and then we can also see that, r is equal to mu1 times lambda, which is equal to, because we know that lambda is equal to mu1 over sigma squared, this is mu1 squared over sigma squared, which is mu1 squared over mu2 minus mu1 squared. So all I've done here is, again, just invert that expression. So we end up with, so I'll just use this notation here. So theta 1, so I'm going to write it all out. So theta 1, theta 2, which is just r lambda, that equals mu1 squared over sigma squared, and then mu1 over sigma squared, or equivalently, you can think of it as mu1 squared over mu2 squared, mu2 minus mu1 squared, and then mu1 over mu2 minus mu1 squared. So this is our g function. So it looked a bit technical, but all I've really done here is invert this expression. So we've got our g function from our h function. Okay, so now we want to calculate these the method of moments. So we know that mu hat 1 equals okay, and then we know that mu hat 2 is just is 1 over n summation xi squared, and then I'm also going to add sigma hat as an estimator, because that's useful here as well. We know that that's just equal to mu hat 2 minus mu hat 1 squared, which is okay, and so that means that we know that r hat mm is just mu hat 1 squared over sigma hat squared, which is just sigma hat mm squared, and which is just x bar over sigma hat mm squared. Okay, and if you want, you can write this out as okay, so this gives you the method of moments estimate this gives you the method of moments of estimates in both the gamma and the normal case, where you have two parameters that you're interested in estimating. So far we've really focused on the question of how to find that theta hat, and as I mentioned, it basically involves first calculating the moments, which is an integration, and then inverting the expression to find the theta in terms of the moments, and then just using the data. So this is what we've looked at so far. Okay, so an important question is, if you tell someone, okay, here's a procedure that you can use to estimate things, then to estimate, say a population mean or some other population parameter, that's great. But then someone's going to be asked, well, how much? Someone's naturally going to ask you, like, how much do you trust that? Like, is it accurate? And so Okay, so the other really key component whenever you're developing any statistical procedure is that you also need to then be able to, find an approximate distribution or some sort of notion of confidence intervals for around theta hat mm for theta. Okay, so then the question is, so how do we do this? How do we, not only just give you an estimate, but also then give you some sort of asymptotic distribution? And so I'm not going to be too precise here, but I'm going to sort of show you how to do that in general, and we'll see that for a couple of examples. So we know that by the central limit theorem, we know that square root of n, so we know that mu hat 1, which is the first moment, satisfies and so you can also extend that to general K. So for if we have that this is mu hat K, which is the kth sample moment. So this is the so now you'd have variance of xi to the k. That should also, sorry, this is an asymptotic result. Okay, so we know that if our n is kind of large enough, we can have this approximate distribution that mu hat k is approximately, so I'll use this notation, approximately normal with mean e of xi to the k. So this is like our population mu k here. And then we get that the variance is going to be the variance of xi to the k over n. Okay, so remember we again get this n here because we have this n right up here. Okay, and so this, you can also interpret this as the squared standard error. So we're going to introduce a term that you may have seen before, which is just the standard error. For an estimate. So the standard error for an estimator is simply, so if we let theta hat be an estimate for if we let theta hat be an estimator for theta, then it's we're going to use this notation. SE of theta hat is, and it's just going to be the it's just the variance of theta hat over n. Okay, and then another thing to note is So this is something we'll see with a couple of examples shortly, but the variance of theta hat will almost always depend on theta as well, but you can also plug in theta hat for that if and when that's needed. So and this gives us a general procedure to find confidence intervals. So if we wanted to find 1 minus alpha times 100% confidence intervals, for theta, so, typical examples might be alpha equals 0.05 gives 95% confidence intervals. Then we can do that by using the so using the normal approximation / the central limit theorem, we can do that by saying that theta is going to be theta minus, and then I'm going to use this term z alpha 2 times standard error of, so this is going to be theta hat okay, so sorry. So z alpha of 2, use z table to find z score for alpha over 2. So for example, if alpha equals 0.05, so for 95% confidence intervals, your z alpha over 2 equal to 1.96 or approximately 2, and you can kind of do this for any value of confidence intervals you want. So now if we want to use this to find confidence intervals for method of moments, for theta hat mm applied to theta, we just have the formula that okay, so if we can calculate, so after we find theta hat mm, which we've learned how to do in the the previous 2 lectures, and need to find z alpha over 2, which just comes from the normal table, and the standard error of theta hat mm, which is equal to the square root of the variance of theta hat mm divided by n. Okay. So let's see some examples. So we're gonna start with the Poisson distribution, which we've already calculated the method of moments estimate for. So we know that lambda hat mm was just equal to x bar, right? And then if we want to calculate, so if we want to find 95% confidence intervals for lambda, we know that the lambda hat mm equals the x bar, which is 1 over n. Then we know that this is actually, I've made a mistake here. This should just be, so I've made this mistake in a couple of places, so let me just correct that. The variance of theta hat mm, and there's no n in there because the n's actually factored in because we use that in our estimate, and I think that's the only place. So let me just correct it here as well. So there is no n here either. Okay, so the variance of lambda hat mm we know is the variance of and so that's just we know that that's just the variance of xi over n, and that's where the n comes in because you have n samples that we're going to use in the method of moments estimate. And we also know that the variance of a Poisson, you can look this up or you can calculate it as just lambda over n. So our SE of lambda hat mm is equal to lambda over n square root, but then you don't know what our lambda is, like that's what we're trying to estimate. And so you can use this pretty good approximation that we're just going to plug in lambda hat mm over n. So to find 95% confidence interval, so we know that z alpha over 2 is 1.96. Then we know that so this is just equal to the square. Okay, and if we were to use, if we were to find a different, say a 90% confidence interval, that 1.96 would go to a lower number, like I think maybe 1.7 or something like that. Okay. So let's let's just be a little bit more concrete here so that we can see some real numbers. So if we consider an example where x bar is equal to 4 and n equals 100, if we want to find a 95% confidence interval for lambda, we get that okay, and so when you do the calculations, you should roughly get 3.8 to 4.2. So the confidence interval is reasonably tight because 100 samples is enough for us to be reasonably sure that if the sample mean is 4, that the population mean or lambda should be relatively close to 4 as well, give or take a little bit, as we can see. So this is just giving you a concrete example where we use the method of moments estimate to to find a confidence interval. Let's do one more example. So this is another example where I've already done this calculation. So we know that the method of moments estimator is is 2 times x bar, or you can think of that as 2 times mu hat. And so if we want to find a 95% confidence interval for theta using theta hat we again just use our formula. Okay, and z alpha over 2 is 1.96 again, because we're again talking about a 95% confidence interval. And if we want the SE of theta, the standard error for theta hat that's going to be just the square root of the variance of and so that's just the square root of the variance of 2x bar which is 2 times the square root of so I've taken the 2 out. When you take it out of the variance, it gets squared, and then I take it out as the square root, so it gets unsquared again. So then we're going to get that this is just 2 times the square root of variance of xi over n. So again, this is the n appears because we're taking an average of n samples, and when you do that for the variance, that gets squared, and so that's why we end up with the variance of xi over n, as we see here. And this, again, is something you can calculate or use the formula sheet for. This is just going to be theta squared over 12 times n. And so you're just going to get so there's just going to be theta times 1 over square root of 1 over 3n. Okay, and so our 95% confidence interval is going to be, well, so I should just say one more thing before continuing, which is that since theta is unknown, you can plug in theta equals theta hat which is equal to 2 times x bar for the standard error. Okay, and so this is the confidence interval that you end up with, and you get a 3.92 here because this is just 1.96 times 2. Okay, and so we've used the we've again used the general sort of approach of finding the z-score and then calculating the standard error to give to find a good confidence interval for that. And once you can, as you can see that as n gets large, we can see that confidence intervals get pretty small. So this is exactly what we want. Okay. So just to summarize what we've done, so this is kind of a reasonably big topic, which is the procedure for finding method of moments estimates. So we developed a general procedure for finding the method of moments estimate. And this is for one or more parameters. This is for one or more parameters. How to find confidence intervals. So using theta hat mm. And so some natural questions to ask is like, so natural ask is, are there, this is a general procedure that seems to, give us something and work reasonably well. A natural question to consider is, are there any procedures that can do better? And so that's sort of a segue into what I'll cover in the next lecture, which will be, maximum likelihood. And that's one of the most widely used procedures because it turns out that it's often, ends up being one of the best procedures. We'll see the method of moments is actually pretty good too, and is also widely used, but maximum likelihood's a principle that actually often tends to give you results that maybe have less variability and tighter confidence intervals, and so we're going to go into that in the next lecture. Okay, thanks very much. That's it for this lecture.